Okay, I hope it works now. Maybe a little too much. We're talking about adiabatic demagnetization. And the process is one in which you start with a magnetic material. That shut it off. Unbelievable. Yeah, I think we got it. We start with a magnetic material and subject it to a very, very strong magnetic field, lining up all the magnetic dipoles that are in the system. Then we thermally insulate it and then turn the field off. And what that does is zap it down to temperatures less than generally 0.01 degree K. That got William Joke at Berkeley the Nobel Prize for Chemistry in 1949 and established once and for all the validity of the third law of thermodynamics, since we could make measurements now down to those low temperatures. The second one, you're asked here, when Faraday tried to liquefy gases, he found that some could not be liquefied no matter how high the pressure was, and he termed these permanent gases. Why wasn't he able to liquefy them? Well, it's because that the room temperature at which he was attempting to apply the high pressure was above the critical point temperature. So there is no liquid at temperatures above the critical point temperature. So no matter how high a pressure you could apply, there's no chance ever that you could get a liquid out of it. Third, here you're asked to state what is meant by a reversible work mode and give an example of a work mode that is not reversible. Well, reversible work modes are ones that can be carried out at an infinitesimal rate so that you only have a differential driving force. An example of one that is not possibly reversible is the one called tangential boundary motion, or work of stirring. Anytime you have a friction involved as the source of your resisting force, then that is not a possible reversible work mode. Because at an infinitesimal rate, those types of resisting forces go to zero. Any question about any of these? All right, we've got, for the remainder of the test, I gave you a lot of information here about a particular gas, fluid X actually. The properties, I give you the critical point properties, critical temperature and pressure, the second variable coefficient as a function of temperature. Give you the ideal gas heat capacity, so evidently we can see this gas is a diatomic gas. And I give you Antoine's equation, and then for reference I give you values of R. And lastly, the absolute value of the entropy at the standard conditions of 25 C and 1 bar, which is 190 then joules per mole K. Actually, just to tell you, this is the data for HCl gas, but I've rounded off all the numbers to make it the calculations easier and then called it fluid X. You're asked, first of all, to evaluate the boiling point of liquid X at 1 bar and the corresponding heat of vaporization. Well, we have Antoine's equation, so I can just invert that to solve by setting the pressure equal to 1 bar and invert that and get a temperature here of 185 K. From the Clausius, then to get the heat of vaporization, I start with the Clausius-Clapeyron equation. And I can write it as explicit here for the heat of vaporization as RT squared times the derivative, temperature derivative of log of the vapor pressure. And when I plug in the numbers for that from the Antoine equation, I end up with 16,738 joules per mole. I also gave you a formula for that in terms of the constants here, A, B, and C. And you could have just plugged that right in, looking at that format, and of course got the same result. Asked next year to evaluate the eccentric factor omega for the fluid, and of course the most important thing is remembering the definition of the eccentric factor, which is minus 1.000 minus the common log of the reduced vapor pressure at a reduced temperature of 0.7. So there are a number of things there to consider. First, we want to be able to calculate the vapor pressure at a reduced temperature of 0.7, and that is a temperature here of 227 K, because I wanted at 0.7 times the critical temperature. So then I plug in the Antoine equation, the 227.5 K, and get that the vapor pressure is 7.389 bars. And then the reduced vapor pressure under those conditions turns out to be 0.08796. And when I take a common log of that, I get, of course, a negative number, minus 1.0557. So when I work it out from the definition, I get an eccentric factor here, an eccentric factor here of 0.0557. Next, you're asked to evaluate the absolute molar entropy S of fluid X at a temperature of 200 K, pressure of 10 bar. Well, right away I know it's a gas. I've already calculated the boiling point at 1 bar is equal to 185, so I know it's a gas. So there's nothing involved here with a liquid. Since state 1 is an ideal gas at 298 1 bar, you were told it was an ideal gas, that initial state was, for which I gave you the absolute entropy, was an ideal gas state. And there we have it's equal to 190. So S2 is going to be whatever that S1 value is, plus the entropy change in going from state 1 to state 2. And that we always work out the same way. It's going to be equal to then minus the entropy departure in state 1, plus when any change in the entropy that takes place in the ideal gas state, and there it is, Cp over T dt, integrated from T1 to T2, minus R log P2 over P1, plus then a departure in the final state. Well, that final state we expect pressure here rather high, 10 bar, so we expect that that's going to be a non-ideal gas state, so we would have to evaluate it. And you're given information on the second variable coefficient, so you have the means to evaluate it. So there are a number of pieces in this equation. This is the S1 is, of course, 190 joules per mole K is given. The departure in the initial state is 0 because it's an ideal gas. And the Cp over T dt integrated between T1 and T2. Luckily here we have the heat capacity is just a constant at 7/2 R. So that works out to be minus 11.62 joules per mole K. Then the minus R log P2 over P1, that just means plug in the numbers and do it, minus 19.14. And then a little more work here for the departure here. This would be actually for state 2 in our case here for a Pitzer gas is minus dP dt times P2. And you did this calculation was actually done in one of your homework problems, so you could go back and take a look at that where we differentiated the second variable coefficient. But I do it here again, as you can see. And you plug in and end up with 6.09 cubic centimeter per mole K. So again, this should be a 2. And we work that out, and we get minus 6.09 per mole K. So putting all the pieces together, we get a value here of 153.14 joules per K. If you did all of this, set it up right and got the wrong arithmetic, I gave you full credit. I didn't take anything off for arithmetic mistakes. The last problem, you're asked to reduce the derivatives partial g with respect to t at constant v, and the second derivative of g with respect to t at constant v. So we see that we've got the abstraction here in the numerator, so we start with the fundamental equation and build a derivative. So I write dg as minus s dt plus vdp, then divide through by dt, and then impose constant v afterwards and end up right away in a one-liner with minus s plus v times partial p with respect to t at constant v. So the second one is just going to be the temperature derivative of what we got up here. So we split that out. That's the temperature derivative here of dg dt at constant v. So then I'll plug that result in here and then carry out the indicated differentiation. But here I've got an abstract derivative ds dt at constant v that I need to reduce. Well, I see it here. Quickest way, there's a number of ways you could do that, but the quickest way I think is just to build it out of the expression I've got for ds here. this is a constant B, so I see right away that term goes out and it's CV over T, and I can just get it by inspection. And end up then with this result. Any question about this? Are the exams still going around, or where are they? Okay. I don't want to forget to pick up the unclaimed ones. Okay, well, now we're ready to move on to our next major topic. Which is the properties of multi-component systems. And here's some reading. I posted this reading assignment as well, but I'm writing it here so that I don't forget to mention that. So multi-component systems mean what they say. It means that a system consists of more than a single component. And if you notice that everything we've dealt with up to this point has been considered to be a pure component, subjected to all kinds of things. And now we're going to deal with these multi-component systems. So if we look at the extensive properties of these systems as functions of their composition, we need to regard them as open systems. So let's note that that's what we're doing here. And then I can express the extensive properties as functions of, let's say, the temperature and pressure. So I'm fixing the intensive physical state, and then the mole numbers, so N1, N2, on to N, capital N, assuming I've got capital of N components. And I could do this for any of the extensive properties. For example, H could be written as H as a function of T and P, N1, N2, on to N sub N, and so forth. And I could do that for any of the extensive properties of the system. For molar properties, I could write things like little b here as a function of T and P, and then the mole fractions. So that would be Y1, Y2, on to Yn minus 1. Because, of course, the mole fractions sum to unity, so I only have N minus 1 of them being independent. I could write, for example, H is a function of Tp, Y1, it's supposed to be a comma there. Okay, so let me make some notational indications here. I'm going to use Y's for mole fractions in a gas phase. And use X's for mole fractions in a liquid phase. And if I don't know what phase it is, I'll use X. But this is the general notation. And then we use the word mixture. That's a generic term, and that's a multi-component system of gases or liquids. But the word solution is more particular. When we use the word solution, we're talking about a single-phase multi-component liquid system. Okay, now what we want to proceed to is an examination of how do we describe these kinds of systems. And we see that they depend on the number of mole numbers or on the mole fractions. And it turns out to be convenient for us to go back and look at the way that they depend on these things, on the mole fractions or on the mole numbers. And that causes us to introduce the concept of partial molar properties. Now I can write out, get an idea of this. If I write out an expression for, let's say, the differential change in one of these extensive properties, and I'll use volume as an illustration, but I could have done it for any of the extensive properties. I could write, for example, that dV, can expand it out, is going to be equal to, given the equation that I had above there, partial V with respect to T at constant P and all the mole numbers, dt, plus partial V with respect to P at constant T and all of the mole numbers, plus partial V with respect to N1 at constant T and P and all of the n's I not equal to 1, dN1, plus similar terms for the other mole numbers. And so what we can see is I can describe these changes that occur with composition are embraced by terms of this type. These are so-called partial molar properties. So this is what we call the partial molar volume. Now I want to examine that idea a bit more closely, so let me make a diagram here. So assume that I've got some vessel with my system in it, and it's got a volume V, and we're at some temperature and pressure. And I want to consider what happens to the system volume when I add just an increment of a component, let's say component I, to the system. So I'm going to add dNi to the system and concern myself with then what is the incremental change in volume with the system that I created by adding that trace of component I. And so that dV of the system is going to be this partial molar volume for component I times dNi. And I've introduced the notation here for that. VI, capital VI with an overbar. Is what the notation that we use for the partial molar volume. So that is partial V with respect to Ni at constant Tp and all n's, say Nj, not equal to I. I'm not sure why this is giving me problems, but it's shutting itself off. Yeah, now it's back on even though it's got a red light. This is the notation we use for partial molar properties. It's consistent with what Koretsky uses. Well, you may, when you look at this, you say, well, this should just be trivially, the partial molar volume should be just trivially equal to, why isn't that just the molar volume of pure component I? If we add a certain amount to the system, why don't we just increase its volume by whatever the molar volume is for that particular component times the number of moles that we add? And this is sometimes true, but not always. I'm sorry. It's just not working.
We'll get it next time.
Even though we got, I put in new batteries and everything, but so we can imagine that we can identify behavior of our multi-component system here with the partial molar properties of the components of which it consists. And so these are all, we should recognize, intensive properties of the system. Now let's explore this possibility. You would think that, does everyone understand me? You would just expect that we would add, if I add a mole or something to it, I would add the molar volume of that to the system volume. That's what I might expect. But this isn't always true. Let's look at an interesting example. And that, you get that written down here. 50 milliliters of ethanol plus 20 milliliters of water equals 67 milliliters of solution. It's interesting, isn't it? So we actually had the solution shrink from the volume that you would get by just adding the volumes of the respective amounts of the pure components. So that means we can't make this assumption, but we'll look at circumstances in which this may be true. And you'll notice that what this calls for, the definition of a partial molar property, like the partial molar volume, requires that I have constant intensive state. And what that means is constant temperature and pressure, of course, but also constant composition. So the relative amounts of the components have to stay the same as I'm doing this. Well, if I'm adding a differential amount, I'm not going to disrupt that.
I'm sorry,
As
can
long
you
as I
repeat that?
Pardon?
Can you repeat that definition?
What?
Can you repeat that?
Yeah. I have to have, to the defining equation here for a partial molar property requires that the derivative be taken at constant intensive state. So that means at constant temperature and pressure, but also constant composition, which means that the ratio of the mole numbers has to remain the same while I'm doing that addition. Well, you say, well, I'm disrupting component I because I'm adding a little bit of component I to it, but it's differential amount, so that does not disrupt it. Yeah.
Well, okay, I was gonna say with the notation up there, your dj not equal to I, that doesn't change, even when you're adding
Right.
component I, but the
Right.
dv over
So
dn.
strictly speaking, I'm adding a little bit of I.
Right, so the dv over dni.
Right.
That's part of the change.
I would have preferred, this is the way it's always done, but if it were up to me, I would have written down there constant TP and COMP, composition, and let it go at that. What this means, though, is that I can build up the properties of the whole solution by considering a process where I'm adding all of the components in the same proportions as they exist in the final solution. And if I can do that, that means I'm allowed to integrate to get the total volume equal to summation of the mole numbers times the respective partial molar volumes. Or I could write for a molar volume, that would be summation here. If let's say it's a solution of all the partial molar volumes times the respective mole fractions. And I can do that for any of these, so H is equal to summation of Na times the partial molar enthalpies, or the molar enthalpy would be mole fractions times partial molar enthalpies, and so forth for any of the properties. I could write it out for entropy or anything else. So now let's probe further and make use of the definitions that we've got here to explore the simplest of all possible systems, and of course that's ideal gases. So here, of course, it's an ideal gas, and I have PV is equal to nRT, which is, the N is the sum of all of the Ni that are in there. So if I want to calculate D, if I want to calculate the partial molar V for a mixture here of ideal gases, let me first write the expression for V itself. then carry out the differentiation. Well, I'm gonna do it for VI. Clean that up. Just a second here. Some particular VI. And if I look up here and do the differentiation, RT over P is just a constant. And the derivative of the sum of these mole numbers with respect to one of them, we can see is just going to be equal to 1. And of course, RT over P itself is the same as just VI 0. Might have been a little less confusing if I made that, let's say, component 1. Because I've used I as the index. Yeah,
Can you explain why that term goes to 1, that differential term?
let's see again.
Could you explain why that differential term goes to 1?
Yeah, because all of the other ends are held constant, so the only one that it matters in this case would be N1. So the sum of the Ni is equal to N1 plus N2 plus and so forth. So partial of the summation is just going to be equal to 1.
Okay,
Okay? All the other ends are constant.
gotcha.
There it is. So I got kind of a trivial result here, but I might have expected that. So for ideal gas mixtures, that is an example of where the partial molar volumes are in fact equal to the pure component molar volumes as indicated here. And it may be possible even for non-ideal gases that I still have an ideal mixture because these pure component molar volumes still might be the partial molar volumes, but we don't know that yet. That's going to be explored here as we go forward. So I did it here for volume. Let's take a look at other properties and consider for a while what would partial molar enthalpy be. We're again here talking about ideal gases. And I can say without any further ado that those are equal to the corresponding pure component molar enthalpies. And the reason for that is for ideal gases, we recall that the enthalpy depends only on temperature. So if temperature is constant, it doesn't matter if anything else varies, including composition. So that would be true. So we can make that statement. I also want to make another definition for ideal gases. We can define what's called a partial pressure. Terrible writing. Physically, the partial pressure of a component I in a gas mixture would be equal to the pressure that would be exerted if I alone were present in the entire volume of the mixture. Well, with that, we can work out what that would be, and if we do that, it works out that. Let's do it, so I'll call that the partial pressure of component I. It would be Ni T over the whole V, which would be seems kind of trivial, but now I see Ni over N is just Yi. So YIP. So the partial pressure, writing it down here again, of a component I in an ideal gas mixture is equal to its mole fraction times the total pressure. And sometimes that's used as the definition for the partial pressure of a component in an ideal gas mixture. Here's the important thing I want you to take home, and that is that for anything other than an ideal gas mixture, we cannot define a partial pressure. It is strictly a concept applicable to ideal gases. Okay, well, we started the list here with enthalpy. Usually the next thing that we will consider is entropy. Now here, you might imagine that we might run into something a little bit more complicated, because entropy depends on more, remember, for when we're talking about pure gases, it depends on more than temperature. It depends on temperature and pressure. So we could imagine that it is going to be composition dependent, unlike the partial mole enthalpy or partial mole internal energy. That would also be, let me just write that. That's also true, but for entropy, perhaps not the case. So we have to address ourselves to the calculation of the molar entropy in an ideal gas mixture of some component I. So let's imagine a process that will allow us to do that. So consider the following process, where I'm going to add a mole of pure component I to a very large reservoir of a mixture which has the composition that I'm interested in. So let me sketch a diagram of it and then discuss it a little bit. So here I've got 1 mole of pure component I. And here I have effectively an infinite reservoir of the mixture, which is at the temperature, this is at temperatures T and P, at the temperatures T and P, and with the partial pressure of component I being equal to YIP. Actually, what I'm going to have is a reservoir, which is the ultimate composition of the system that I'm interested in. And I'm looking at component I here in particular, so I could write the partial pressure as equal to YI times P. And I want to consider the process where I'm adding that 1 mole to the mixture. Now, if I calculate delta S for that process, I can write it down. Delta S is going to be equal to whatever the partial molar entropy is in the final mixture, minus what it was as a pure component. So I'm trying to write that as a little bit smaller, little si, 0.